Welcome to this channel. My name is Chris, and today we'll talk about the extension theorem of Caratheodory. And yeah, first of all, we want to repeat some things. What do we want to do now? First, we defined content and measure. And what we want to do now is go ahead and define continuity for contents and measures. Yeah. And then we will extend those to a sigma algebra. Yeah. Okay. So first of all, motivation for the things we will do today. And this motivation is also a very, very important example. So let's take a topological space xt. Yeah, so T is a topology. We call B of xt as defined as sigma of T. So this is the sigma algebra, which is generated by the topology. We call this the Borel sigma algebra. And this is really for Rn the most important sigma algebra there is. So you should memorize it. Yeah, and in the special case of x is equal to Rn and T the Euclidean topology, then one can prove easily that the Borel sigma algebra is generated by open hyperqubits. And yeah, this is a proof where you prove each step by step, so this is not really interesting. You can do that as an exercise, yeah, if you like. Okay, and now we know the following from Riemann integration theory out of the first semester. Yeah, I think. The integral of that is b minus a for two real numbers a and b. And hopefully this is enough for you that you believe me for the moment that if we take this as a measure space, yeah, so on the with the real line, then first of all this is a measure, and the measure of this interval is b minus a. We will make that much more in detail and formal later, step by step, okay? But for the moment, this should be a motivation. And the goal now is to construct a measure on BRN, yeah, out of this measure. Okay. And the first idea that comes maybe to your mind is the following one, and that this might be not a good idea should come to your mind if you think of the measure problem while we're doing this stuff here. So take an A subset of R and define the following outer measure. So sigma star as the infimum of the sum of the measures, where A is a subset of the union of AIs, and the AIs are, yeah, speaking a family of intervals. So what are we doing here? We want to cover the set we're taking, so A in this case, as small as possible with intervals and at their measure. Okay. Yeah, if you look at that, this looks like the right side of the sigma additivity, and this is really not randomly. And what do I mean by cover? It's a cover which you use, for example, if you prove that a set is compact. Yeah? Okay. And it points out that this is not a measure because it doesn't fulfill sigma additivity in general. Yeah? Only a weak one, which one calls sub-additivity or sigma sub-additivity. Yeah, so this is not a measure. Yeah. But as I already said, this is an outer measure. And the problem here is the disjointness we consider for the sigma additivity. If we have two sets which are subsets of each other, then we don't have a problem at all. So we want to solve that now, yeah, because we haven't solved the measurements problem. And also we want some nice properties such as analog to the Banach spaces. So a completeness property, basically. Okay. So let's talk about continuity of contents and measures. So consider a measure space as usual. And then the following holds. If we have a sequence of sets, that's those which are monotone increasing in M. By that I mean that's those are included in each other in an increasing way. So sometimes some guys write it like that with the union in it. Then the measure of it converges to the measure of the union. In some style, this is like a lower semi-continuity for sets. This is not 100% correct, of course, but think of it like that. Yeah, in the analog way, so if we have an as monotone decreasing in M, so like that, and the intersection of it in M, then we also need a property like that. So a convergence property, roughly speaking. So we have an N, and at which the measure is finite. We will talk about that in a few seconds why we need that. And then we have the convergence to the intersection. Okay. So warning, the requirement is important. So as an example, let's define the measure as cardinality of A if A is finite and infinity else. So this is called the counting measure, and that's a good name because we take the cardinality if A is finite, so we count the elements of it, and otherwise will be infinite large. And now we look at an, so as all natural numbers from n to infinity, and we will see that this will be empty, and so the measure is 0, but this will converge to to infinity. So this is not the same. Okay, so this is an example where this fails because it is this requirement is not fulfilled. This short sketch of the proof. Consider this construction and use sigma additivity for the first one, and for the second one use subtractivity of measures. So this is analog to the additivity you might might think of it. Okay. And if a content now fulfills the first statement, we will call it continuous from below, and we call it continuous from above if it fulfills the second. And if it fulfills both, then we call it continuous. Okay, but now we have a few properties open to solve, and those are a reverse reside of the continuity property. So we want a continuous content to extend on a sigma algebra to a measure. Yeah, so that's the reversed reside. Then we want completeness, and we want sigma. Okay, and yeah, you can stop this video and think of it if you have an idea to solve this without looking at this. Yeah, of course. You have my respect if you can solve it, because this is not that easy. We need a very smart idea, and Caratheodory had one. And he defined the following set system, sigma star. So we take all sets, yeah, in an X, for which this property here holds, yeah. So basically you can measure this B here with intersecting it with this A and intersecting it with the complement, yeah. And I want to say the proof that this is enough to solve our measurement problem. This is really hard to prove, yeah. But what we have here, yeah, is really intuitively, and I will show you in a few seconds why. But first, let's tell you that we can also define the set as the following. We can only consider this. This is equivalent because this direction is always fulfilled. This is the subadditivity, the sigma subadditivity I told you. No, it's a subadditivity. And yeah. Okay. Yeah. And what do we have here? Let's say it would be really strange if this wouldn't hold for a set which we call measurable. Because if you look at this picture, yeah, we have B here in R2, and now we want to know the area of it, yeah. And I took also some A's and enumerated them. And what do we want now? We want that the area of B is the sum of this and this. And what is that? So we have this intersection here. And now we need, there's this area left. How do we measure that? We take the complement of that. Yeah. So this space here and intersect it with B. So basically this is really this part. And you can do it for that and that and that also. Okay. Now we can solve the measurement problem, yeah? And this is the extension theorem by Caratheodory. So we consider a content mu which is continuous from below on M over X, yeah, as usual. And this content induces auto measure, yeah? Like that. We take the limit of mu of an, and the an's in M are monotone increasing with a in the union of this sequence. And basically this is really the continuous from below property, if you look at that in some sense. Okay, and the sigma star is as before, so this one, yeah, we discussed a few seconds before. Then the following holds. First of all, the sigma star is an sigma algebra. Yeah, and this, of course, we expect that because otherwise we could stop here. And a sigma star restricted to this sigma algebra is a measure and extends mu. And for all a in M, so in a Z algebra, mu star of A is mu of A. The generating system is in it. And, oh yes, it is true. The measure space is complete. So what do we mean by that? If we take a subset of a null set, then it's also a null set. What do we mean by that? A null set is a set which has measure 0. Okay. Yeah, and if mu is even finite on M, then this extension is also unique in some sense. And you can't expect that this is true in general. If you think of the counting measure, you can construct an easy example where this fails. Okay, and now an example, and a very, very, very important example. So you can show that there's only one measure on the Borel sigma algebra, which is generated by the open hyperqubits out of the motivation. So those, you remember that. And they fulfill this. So if you take this away, you see that it's a one-dimensional form of what we had in the last video. So B minus A. And we call that a Lebesgue measure. And this is the volume measure for Rn. So basically this is the measure which is used by far most of the times. So okay. And what is the idea to prove that? We see that those hyperqubits are a generating system which is stable under intersections. So intersections are also in the generating system. And the uniqueness follows from the continuity from below. Okay. And now you might think, what? Why is this measure finite in general? This shouldn't be true, and you're right. How does that fit into the Caratheodory picture? And the finiteness in here will be fit if we intersect Borel sets, so basically the sets out of the sigma algebra, with an hyperqubit. You can think of that, and we'll see that this is true. Yeah. Okay. That's for today. Yeah, thank you for your attention. And See you in the next video. Bye.